The subject of this lecture is momentum and also impulse, which is a quantity that is related to momentum. Momentum is a physical quantity which is attributed to objects in motion. So objects that do not move, that are at rest, do not have momentum. Only objects that are moving have momentum. So how do we define momentum specifically? Any object with mass m moving with speed v has momentum p equal to the product of the mass and velocity of that object. The formula that relates those three quantities is that the momentum p is equal to the product of mass times velocity. Again, p is the momentum, m is the mass, and v is the speed or velocity of motion. The units of momentum are the units of mass, kilograms, times the units of speed, which would be meters per second. So from those, you can tell that when you're calculating the momentum of an object that's in motion, the mass of this object must be converted into kilograms, and the speed of this object must be converted into meters per second. And so this would be in the metric system. The imperial units for momentum would be the product of the units for mass, which are slug, and the units for speed, which would be feet per second. And so if the units are not those, when you're multiplying mass and speed, you must convert the mass into slugs, the speed into feet per second to get the correct units for momentum in the imperial system. From the definition of momentum, we see that momentum depends on the mass of the moving object and the speed of motion of this object. And so we can have an object that is really small in mass, for example, a small projectile like a bullet, that is moving very fast, and that will result in a pretty big momentum for this projectile. But then we can also have a very large object that is moving very slow, for example, an 18-wheeler, that will also have a very large momentum. Where the notion of momentum is a little counterintuitive is that a super heavy object moving really slow can have actually a really big momentum, because we are used to visually perceive the world around us, and so when we look at objects that are moving, we judge them by the speed with which they're moving, and we are not accounting for the mass of these objects. And so an 18-wheeler moving with 5 kilometers per hour will have a giant momentum, even though it's moving really slow, because of the mass of the truck. Let's look at a comparison example to illustrate the point here. So if you look at a middle-of-the-road Toyota Corolla, it has a mass of 1,200 kilograms, which is 2,646 pounds. If that Toyota Corolla is moving at 60 kilometers per hour, which is 37 miles per hour, the momentum of this Toyota Corolla would be 1,200 kilograms times 60 kilometers per hour, which is 1,200 kilograms times 16.7 meters per second. And that's resulting in 20,040 kilograms meters per second. So that is the momentum of that Toyota Corolla. Now let's look at a Toyota Highlander with mass of 1,974 kilograms at the same speed of 60 kilometers per hour. This Highlander will have momentum of 32,965 kilograms meters per second. If you compare those two momenta to the momentum of a Boeing 747-8 at 60 kilometers per hour, well, the Boeing has a momentum of 7.35 times 10 to the 6th kilograms meters per second. So this is in the millions. And 60 kilometers per hour or 37 miles per hour is not a very high speed at all. But you can see how an object that is moving relatively slow but with a huge mass will actually have a really big momentum. Now let's look at a different example. Let's find the momentum of a bowling ball with mass of 3.2 times 10 to the 3rd grams and speed of 10.8 kilometers per hour. So the mass of this bowling ball is 3.2 times 10 to the third grams, and the speed is 10.8 kilometers per hour. We are looking for the momentum. So I will use the definition of momentum, which is that the momentum P is equal to the product of the mass m and the speed v of the bowling ball. So let's plug in the values for the mass and the speed, and let's see what we get. 3.2 times 10 to the third grams times 10.8 kilometers per hour. So I noticed that the units here are different than the units for momentum. So the units for momentum are supposed to be kilograms meters per second. And so that means that since I have grams and kilometers per hour, if I do the calculation now, that's going to produce an answer with units of grams times kilometers per hour. And so therefore this answer will be wrong. So that means that I have to do a conversion before or after the calculation to get the correct answer. So I choose to do the conversion before the calculation. So let's see what that looks like. So first, I'm listing here the relationships between the units from which I'm converting and the units into which I want to convert. So 1 kilogram has 1,000 grams, 1 kilometer has 1,000 meters, and 1 hour has 3,600 seconds. So I'm going to use those three relations to create my conversion factors. I will apply my conversion factors at the same time to the calculation. So I have 3.2 times 10 to the third grams times the conversion factor that converts from grams to kilograms, which is 1 kilogram divided by 1,000 grams. And then after that I have the velocity 10.8 kilometers per hour times the two conversion factors that will convert the kilometers into meters and the hours into seconds. So first we have 1 hour divided by 3,600 seconds. That converts from hours to seconds, times 1,000 meters divided by 1 kilometer, which will convert from kilometers to meters. So in the conversion of the mass, we have grams here and grams in the denominator in the conversion factor. Those will cancel out. And then for the conversion of the speed, we have kilometers in the numerator. They will cancel with the kilometers here in the denominator. We have hours in the denominator here and hours in the numerator here. Those will cancel out. And so let's see what we have left. So we put everything together. We get 3.2 times 10 to the 3 times 10.8 times 1,000 divided by 1,000 times 3,600. And let's put this in parentheses like this. And the units now will be kilograms meters per second. And after calculating this expression here, I get 9.6 kilograms meters per second. If you did not convert the units, you would get a wrong answer, which would be 34,560 grams kilometers per hour. And so this would be wrong. However, if you went that way, what would you do is then you would have to apply the conversion factors that I discussed here in that conversion to the final answer to get the correct answer, which is 9.6 kilograms meters per second. The other quantity that is related to the concept of momentum is impulse. Impulse is simply defined as the change in momentum of an object. And so if I wanted to express this as a relationship, that would read as the impulse is equal to the change in momentum p of an object. So we already know how to calculate the change in a physical quantity. That would be the difference between two values of the quantities, which we will call a final and initial value. So the change in momentum would be the difference between some final value of the momentum of a moving object and some initial value of the momentum of a moving object. And we also label this difference here as delta p. So now what we need to discuss is what is impulse exactly. Well, when we talk about impulse, we talk about the impulse of a force. Why a force? Well, if an object is moving with certain velocity, that means that this object will have some momentum, which is just the product of the mass of the object and the velocity of the object. But how can the velocity of the object change so that its momentum changes? Well, the only way the velocity of the object will change is if a force is applied to this object. So when a force is applied to the moving object, its velocity will change. And the change will happen until the force is no longer acting on the object. So then that means that not only it's important to know how much force is applied to the object, but also for how long was the force applied on this object. And so the combination of the amount of force and the time of application determine the impulse that was responsible for the change in momentum, delta P. And so the definition of an impulse of a force is simply the product of force and time of application. So this is force times time. Or in other words, impulse is equal to F times T. What would be the units for this quantity? Well, those would be the product of the units of force. In the metric system, that would be newtons times seconds, or Newton seconds. And that's metric. And in the imperial system, that would be pounds seconds. And so now I can put together the two quantities. So on one hand, I have that the impulse of a force, which is the product of force and time, is equal to the change in momentum. And so I can put the two together to get a final expression which I can use for calculations in regards to impulse and change in momentum. And so this final expression is that F times T is equal to P final minus P initial, or in other words, F times T is equal to the change in momentum. And so this is the two formulas that can calculate problems involving impulse and momentum. So the first version of the relationship, force times time is equal to final momentum minus initial momentum, is useful when we can calculate the values for the momentum of the object at two different moments of time. The second version of the formula is useful when we know only the change in momentum, but we do not know the individual momenta at two different moments of time. So we know the change already. So then we use the second formula. So let's do an example. So let's look at a car that has a mass of 1,000 kilograms, and at some point during its motion, which I will call the initial position, the car has initial velocity of 10 meters per second. So when the car is at this initial position, I will start, counting the time that it's going to take for this car to get to some final position. So the car is at this final position now. The mass doesn't change. We will assume that the car hasn't moved, long distance enough to lose significant amount of fuel to be weighing less, have more mass. So the mass remains the same, but now the velocity of the car is different. Final velocity of 20 meters per second. So the velocity changed from 10 meters per second to 20 meters per second. And I also measured the time for this change, and so the time would be 5 seconds. So it took 5 seconds for the car to increase its velocity from 10 meters per second to 20 meters per second. So for the car to change the velocity from 10 meters per second to 20 meters per second, there must be a force acting on the car. So some force acts on the car during that interval of time. And then after that, it may be acting on the car still, or it may not be acting. We don't know, and we don't really care. We only care what happens between those two positions as the car is moving. And so where would that force come from? Well, it's very simple. For a moving car, that would be the driver is pressing the gas pedal, for example. So the car accelerates, and that's why the velocity changes from 10 meters per second to 20 meters per second in this particular example. Okay, so now I know everything about this situation except for what is this force, how big is that force? And so that is the question that I want to answer. So the question here is, how big is this force? Okay, so I know that there is a relationship between the change of momentum of this car and the force that's applied. And this is that the impulse of this force is equal to the change in momentum. So the product of the force and time for which the force was applied on the car is equal to the change in momentum. So the change in momentum is simply the mass times the velocity at each moment of time. So that would be mass times final velocity minus mass times initial velocity. And so, since I'm looking for the force, I also will move the time from the left side of this relationship to the right side of this relationship. And so since the time is multiplying here on the left side, I must divide by the time on both sides to get the expression for the force. And so force is equal to mv final minus mv initial divided by the time. Okay, now I have all the information necessary to calculate the force. I just need to substitute the numbers in that expression here. Let's do that. So I get 1,000 kilograms times 20 meters per second minus 1,000 kilograms times 10 meters per second divided by 5 seconds. So the masses here are in the correct units of kilograms. The time units in the speeds and for the time elapsed are all the same, so they're compatible. Everything is in seconds. So then I can start doing my calculation. So from the first term I have 20,000 kilograms meters per second. From the second term I have 10,000 kilograms meters per second. So the difference is 10,000 kilograms meters per second divided by 5 seconds. That is 2,000 kilograms meters per second squared, which is what we call newtons. And so the force is, by magnitude, is 2,000 newtons. So a word about the units of impulse. So impulse is the product of force and time. And so the units for force in the metric system are newtons. And the units for time are seconds. So impulse has units of Newton seconds. But on the other hand, that is also equal to the change in momentum. And so for change in momentum, the units are kilograms meters per second. So since impulse is equal to change in momentum, that means that those units are equal to each other. And so we can say that Newton seconds are equal to kilograms meters per second. It is the same thing. So this is a side note just to sort of get your attention on that point. for future calculations. Let's talk a little bit about the applications of the relationship between the impulse of a force and the change in momentum for a moving object. A very important application is in car safety. So let's look at the relationship between impulse and change in momentum one more time. So we know the product of the force and time over which the force was applied is equal to the change in momentum. So consider a moving car that collides with, let's say, a wall, hits a wall. So then the change in momentum will be from whatever the initial momentum was at certain velocity to essentially zero if we approximate the collision with an instantaneous stop for the car. Okay, so if the car stops for almost no amount of time, that means that on the left side the time interval here will be very small, which then means that in order for this momentum to change from some finite value to zero, a huge amount of force must be applied to the car. Okay, so for a person that's in this car, they are also moving with the same momentum as the car since they are sitting in it, and they are also going to have a change in momentum the same as the change in momentum for the car, which then also means that they are going to experience the same amount of force on their body as the car did. And the human body is brittle, and when the change in momentum is big enough, that is going to cause injuries. All right, so then how can this change in momentum be sort of modified so that smaller force is applied to the body of the passenger in the car? Well, if the time of stoppage is increased, then that means that smaller force will act on the body since the change in momentum is the same. How can this be achieved? Well, if the car has an airbag, when the person hits the airbag, that is going to increase significantly the amount of time necessary for the body of that driver or passenger to stop moving, to slow to a stop, which then means that this passenger will experience much smaller force, which then can result in less injuries or no injuries at all. So the change in momentum of a moving object is equal to the product of the applied force multiplied by the time of the action of force. And so if the time increases, the force can decrease for the same amount of change, and vice versa. Another example of this principle would be dropping a glass on a bare floor versus dropping a glass on a thick carpet. So if you drop a glass on a bare floor, you would expect that the glass will break, and that's most often the case. And the reason for that is that the change in momentum of that glass when hitting the floor happens over a very short amount of time, so a large force is applied and that breaks the glass. But if you drop the glass on a piece of carpet or on a thick carpet, then the same change in momentum will happen over a much longer period of time compared to bare floor, which means that smaller force is applied to the glass, and then chances are the glass will not break. And so to summarize, for car safety, the relationship between change in momentum and impulse of a force is important. We want to minimize the force that is acting on the car and the passengers inside and maximize the time of action of the force. And so to mitigate the force and increase the time, there are airbags, seat belts, and crumple zones applied or utilized in a car safety application. Let's look at this example to calculate that relates impulse and change in momentum. So what is the magnitude of force that is necessary to slow down a 1,450 kilogram car traveling with 115 kilometers per hour down to 45 kilometers per hour in 3 seconds? So we know the mass of the car, 1,450 kilograms. We know the initial speed of the car, 115 kilometers per hour. We know the final speed, which is 45 kilometers per hour, and we know the time for the change in momentum to occur, and that is 3 seconds. The question is, what force must be applied to the car for this change to happen? So here let's look at the units first. So we know that momentum has to be calculated in kilograms meters per second. So the mass here is in the correct units for the calculation. But the two speeds, the initial and the final, have units that are not the correct units for the definition of momentum. So the units must be meters per second instead of kilometers per hour for the calculation to give the correct result. So the first thing that needs to be done here is to convert the speeds from kilometers per hour into meters per second. So 115 kilometers per hour are multiplied by 1,000 meters per kilometer and also by 1 hour per 3,600 seconds. The units of kilometers and hours cancel out, and what we are left with is 115 times 1,000 divided by 3,600. The new units are meters per second, and so this is equal to 31.9 meters per second. Similarly, 45 kilometers per hour comes out to be 12.5 meters per second. So now that the conversion is done, I can calculate the force that is needed to slow down the car. So the force would be equal to mv final minus mv initial divided by the time. So I will substitute all values in this expression and find the answer. And so we have 1,450 kilograms times 12.5 meters per second minus 1,450 kilograms times 31.9 meters per second divided by 3 seconds. The numerator is equal to negative 28,130 kilograms meters per second. We divide that by 3 seconds and we get that the force is negative 9,376 newtons. However, the question was, what's the magnitude of the force? And so therefore, we ignore the minus. And the final answer is that the magnitude of the force is 9,376 newtons. So what is the meaning of this minus sign here? Well, the meaning of the sign is that as the car is moving in one direction, let's say to the right, the force that acts on the car to slow it down from 115 kilometers per hour to 45 kilometers per hour acts in a direction opposite to the direction of motion. The car is decelerating. That's why the speed is decreasing. And since the calculation requires to calculate the change in momentum, the difference between a final value minus initial value, the final value is smaller than the initial value, we get this minus sign. But this minus sign really tells us that the force acts in a direction opposite to the direction of motion of the car. So this is a consequence of the fact that force is a vector quantity, which was a quantity with magnitude, in this case 9,376 newtons, and direction. It is directed opposite to the direction of motion of the car. Let's do one more example. So we have a 10 Newton force which is applied for 3 seconds on a box that is placed on the floor. The question is, what is the change in momentum of the book due to that force? So this problem is a little bit different than the previous examples because we know the force and the time of application of this force, and what we're looking for is the change of momentum, the difference between final and initial values. Okay, here we do not have any information about the mass of the box. We have no information about the velocity of the box before and after the application of the force. All we know is the force applied for how long was the force applied, and then we are asking for the change in momentum. So this problem requires to use the other formula that I gave you for the relationship between the impulse of a force and change in momentum. And that was that force times time is equal to the change in momentum. And so this problem here is very straightforward to do. I just need to multiply the force by the time to get the change in momentum. So that is 30 Newton seconds. And that's it. I don't need to find any velocities or masses or nothing like that. That's not what the question is asking. One more point that I wanted to make is that the units right now for the change in momentum are the units that come from the units of the force and the units of time, so Newton seconds. But I mentioned before that this is also equal to the units for momentum. So this answer can also be written as 30 kilograms meter per second. It is the same quantity expressed in different units. Alright, so this concludes the lecture on momentum and impulse. You guys will get to apply those concepts when you do the worksheet on that chapter. Make sure to write down the formulas that I discussed in this lecture to have them handy for the work on those worksheets.